Good afternoon, everybody. Happy Friday. Happy Halloween. Welcome to lecture. So the exam's graded and everybody got their exam back. The key has been posted for both versions of this exam. They just accidentally happen to be the same this time. That was a clerical error. I accidentally printed out the same copy. I put one of them on blue paper, one of them on green paper. But so anyway, don't let that confuse you. Usually they're different, but this time they weren't. The statistics for the exam are here. The exam performance was really good. The class performed very well. The average was over 82%, which is really high. I am impressed, really impressed, especially when you look at the distribution here. So this is a histogram that shows the percentages that people got, and it's kind of a wide distribution, but when you get up to the 90% range, there were 14 people that were over 90%, and that's almost half the class, which is something I rarely see. So just as a class member, give yourself a pat on the back. The class did really well. If you're down here, certainly you can do better, and we can talk about methods to improve, but overall the class is really, I think, getting it really, really well, with a few people that are struggling a bit, but overall really good. So whatever you're doing, especially if you're up in this range, right up in here, just keep doing it because you're doing really well. So now we're going to go on and talk about some additional stuff in aromatic chemistry. So electrophilic aromatic substitutions, the theme that we've been going with. And I want to show you a survey question that we had from last time. So in this survey, it was asking which structure, A, B, C, or D, is not a resonance structure of the non-aromatic intermediate in the chlorination of benzene. So this was a mechanism that we talked about last time where chlorine sticks bonds to FeCl3, that's iron trichloride, that activates the chlorine, and then the ring pi electrons attack it, and you get a non-aromatic intermediate. And it has several resonance structures. There are 3 of them up here. The legitimate resonance structures are A, B, and D. C is not a legitimate resonance structure. It's got the positive charge on an sp2 hybridized carbon. So it looks similar to B, but it's really not the same. It's not even close, really. This cation is really stabilized by resonance. It's got 2 double bonds that are next door and can delocalize the charge. In this structure, the positive charge is not resonance stabilized, and it's a very unstable positive charge. And I was really happy to see that almost everybody got this one right. 91% was the result for the correct answer, C. So nice job. I feel like that is clicking with people. So that is good. And we'll continue talking more about electrophilic aromatic substitution today. But are there any questions about the stuff we talked about last time, or electrophilic aromatic substitution, or this survey question? All right. Before I turn the projector off and switch to chalkboard mode, I want to show you one more picture. This is straight out of the textbook. It is a list of activating and deactivating groups in electrophilic aromatic substitution. So we're going to talk in the later part of the lecture today about how substituents affect substitution. When you put a group on a benzene ring, what does it do? Does it make it go faster or slower? Does it have a directing effect? And the answer is always yes. The group does something. And this is a list of exactly what these different groups do. We'll come back to this when it'll make a little bit more sense, but you'll see the groups listed here vertically in order of their activating tendencies. So the ones at the top are the strongest activating groups. As you go down, the activation decreases. These are ones that make the reaction go faster. So if you have one of these groups on the aromatic ring, it makes substitution go a lot faster. And you get down to the point where then this black line says things below that are deactivating groups. So X, where X is halogen, these are mild deactivating groups. And then as you go lower, the deactivating groups get more and more powerful. And then to the point where you get down to the bottom, and these are very deactivated rings. The dotted line is telling you something about the directing effects. So the dotted line marks the point at which the directing effect switches from being what's called an orthopara-director to a meta-director. So if you've got a substituent on the ring, like say an R group, an alkyl group, that is an orthopara-director. In other words, it makes substitution want to happen in the ortho and para positions relative to it. But you get below that, and then the groups start to activate, or not activate, but start to direct to the meta positions relative to them. So if you've got an aldehyde on the ring, the substitution wants to happen in the meta position relative to it. And so you don't need to memorize this, but you need to just be familiar with the table and understand how it works. We're going to talk about the theory that explains why these groups do what they do. It has to do with the way that electron density is either pushed into the ring by the activating groups or pulled out of the ring with the deactivating groups. And we'll talk about that in some detail. So this is coming up, but I wanted to give you this resource. It's in the textbook. It's posted in Canvas. It'll be an attachment on the next exam. So let's talk about electrophilic aromatic substitution some more. Last time we talked about a bunch of different reactions that put groups on benzene ring. We looked at chlorination and bromination. Then we looked at nitration. Then we looked at sulfonation, and we went through their mechanisms. We talked about how active electrophiles form, and then how the active electrophile gets attacked by the ring electrons, the pi electrons on the ring. And then we talked about how the non-aromatic intermediate that gets formed gets deprotonated to restore aromaticity with the substituted ring. Let's continue on with that. With a new class of substitution reactions called the Friedel-Crafts reaction. So that's where we're going to start. So Friedel-Crafts reactions are the next topic, and they add carbon groups. Which makes them really important in synthesis, in organic synthesis. So a lot of times the tricky part in putting molecules together is making bonds to carbons, building the skeleton. So these are really valuable techniques, reactions for doing that, installing carbon groups. And there's two types. There's Friedel-Crafts alkylation, that adds an alkyl group. That's one class, and it looks like this. The way that these work is you'll start with an aromatic ring, and it could be benzene. That's where we'll start. We'll expand it to substituted rings really soon, but for starters, just to keep things simple initially, we're going to just look at benzene. When that gets put in with an alkyl chloride, RCl, and then aluminum chloride, here R is equal to alkyl. So it'd have to be some sort of alkyl group, like a methyl or an ethyl or something like that. And the aluminum chloride is a Lewis acid catalyst. These conditions give a substituted ring where the ring has got a new bond to an alkyl group. And the other product is HCl. So that's Friedel-Crafts alkylation, puts alkyl group on the ring. Then there's Friedel-Crafts acylation, which I'll put on this next board. And this reaction adds an acyl group, which I will diagram here, and then I'll point to it so that you know exactly what I'm talking about. But here's the way it works. If you start with an aromatic ring, like say, for example, benzene, and you put in a reagent called an acid chloride. Acid chlorides have a carbonyl group that has some sort of R group attached, but they have a chlorine. So this is called an acid chloride. It's a special kind of functional group that we're just getting introduced to now, and we'll talk more about it as we go through the course. But the other thing that needs to be in there is a Lewis acid aluminum chloride. And when these things are together, what comes out of the reaction is you get a benzene ring, aromatic ring, but you get an acyl group attached. So the ring has been acylated. And the other product is HCl again. So this is an acyl group. And the R group is some sort of carbon group. It could be methyl or ethyl or propyl or phenyl or some kind of carbon group. But these are the two carbon bond forming reactions involving aromatic rings that we're going to talk about. So any questions about this so far? All right, well, then we'll tackle the Friedel-Crafts alkylation reactions first and talk about their particulars, like how do they work, when do they work well, when don't they work well, are there problems, and there are certainly all kinds of things that you have to worry about with these reactions. There is no perfect reaction in organic chemistry is the thing. I mean, there's reactions that are really good, but all reactions have their strengths and weaknesses, and Friedel-Crafts alkylation is no different. So we gotta know the basics, but then we gotta dig into the details and know exactly when they're gonna work, when they're not gonna work, when things can go wrong, and exactly how they might go wrong. And even then, chemistry can surprise you sometimes. These molecules can be kind of wily beasts sometimes. But let's talk about the mechanism of how this thing works. So this is going to be mechanism of Friedel-Crafts alkylation. So the first step is, like we talked about last time, when you have a reaction, one of these electrophilic aromatic substitution reactions, the first thing that happens is an active electrophile forms. So you put some things together, they react to make a really reactive species that then the ring attacks. And the species that we're going to put together here are going to be alkyl halide and the aluminum chloride. And the thing about this is the mechanism is a little different depending on whether or not you've got a primary alkyl halide or a secondary tertiary alkyl halide. So active electrophile formation depends on substitution. Of the alkyl halide. So the first one we're going to look at is primary alkyl halides. And as the demonstration alkyl halide, I'm going to use ethyl chloride. So ethyl chloride has a methyl group that's attached to a CH2 that's attached to a chlorine. And this is a primary alkyl halide because, remember, the carbon that holds the leaving group, the chlorine, the chloride leaving group, is attached to one carbon group. So we talked about this a lot last semester, but in case it requires a little bit of review, primary alkyl halide, what you do is you focus on the carbon that the halide is attached to, and you count the carbon groups, and if there's one, that's a primary alkyl halide, and it's a very low substitution kind of alkyl halide. Then when you put aluminum chloride in, aluminum chloride is a Lewis acid. What that means is it's hungry to make bonds with things that have lots of electron density. It's got a big partial positive charge on aluminum, and the chlorine is a partial negative charge, and 3 lone pairs of electrons. And so, like happened in the chlorination and bromination reactions, you remember seeing something really similar to this. The lone pair on one of the chlorines in chlorination went and bonded to an iron trichloride. Well, here this chlorine atom is going to use a lone pair to bond to the aluminum. So it's really very similar in this step to the chlorination mechanism that we looked at. We're going to hook a chlorine to the aluminum, and that's going to make it an even better leaving group. So then the result of that is that there's this activated alkyl halide now that's got a chlorine that's attached to aluminum, The aluminum bears a formal minus charge. The chlorine bears a formal positive charge. And effectively what this is doing is it's making this chlorine into a really good leaving group, even better than Cl by itself. Chlorine by itself is already a good leaving group, but when you hook an aluminum to it, it pulls on it, it tugs on it, and this is like a great leaving group. I'll call it a super leaving group. Super. Just to be kind of dramatic about it. And what it does is it makes this carbon really partially positive, so that the ring electrons in the pi cloud are going to be attracted to that carbon. They're going to want to attack it, and then that bond is going to break. It basically helps, the aluminum helps the chlorine leave. All right, so that for primary alkyl halides, this is the active electrophile that you get. It doesn't form a full carbocation. It forms this species that's like a carbocation. It's kind of carbocation-like, I would say. It's not a full carbocation. It's got a partial positive charge on that carbon, but the leaving group doesn't like fully get away. Okay, so that's primary. When you have secondary or tertiary, things are a little different because those molecules can form full carbocations more easily. Remember, the chlorine isn't going to want to leave in this case because it would leave behind a primary carbocation, and those are very unstable because carbocation substitution trends with, or carbocation stability trends with substitution. Highly substituted carbocations are nice and stable, but primary carbocations like this would be, if the leaving group were to leave, those are really unstable, so those don't like to form. So this is where it sits for primary. Then let's take a look at what the secondary and tertiary alkyl halides do when you put them in with aluminum chloride. Oh, I erased the cat. Sorry. Yeah, I didn't mean to. I just like, it's just reflex. Just erase everything. Sorry, Katie. Halloween cat is gone. It was a cute cat. I was trying to keep it, but just, yeah. A catalyst is gone. That. Oh, I kind of like it, even though it's corny. Chemistry jokes are always corny. All right, here's what happens with tertiary carbocations, secondary and tertiary carbocations. Or secondary and tertiary Rx, comma, a carbocation forms, which is a little different. So here's how that works. Here is a tertiary alkyl halide. This is tert butyl chloride. It has the same tendencies as the primary alkyl halides to bond to an aluminum because it's got this electron-rich chlorine. And then aluminum chloride is an electron-poor species at aluminum. The aluminum has a really strong partial positive charge because it has these three chlorines that are pulling electron density away from it. So the chlorine likes to go and make a bond to the aluminum. So this first step in the active electrophile formation is the same as over there. We're going to get an alkyl halide that has an aluminum bonded to the chlorine that's going to tug on it and make it into a super leaving group. The aluminum gets a formal minus charge. The chlorine gets a formal plus charge. And just like I did before, I'm going to lasso this thing and say, this is a super leaving group. It's not a technical term, by the way. It's just me expressing it's an even better leaving group than chlorine by itself. Super leaving group. And it likes to leave. And since it's a tertiary species here, it can form a tertiary carbocation, so it will. And the next thing that happens is this bond between the carbon and the chlorine breaks, and those electrons go to chlorine. And what you get is a full carbocation. In this case, it's a tertiary carbocation, tert-butyl carbocation. We've got a full plus charge on carbon. The leaving group leaves, and what you get floating in solution is the aluminum with the 4 chlorines attached and a formal minus charge on it. So that tertiary carbocation is the active electrophile. That's what the ring is going to see. That's what the ring is going to attack. So there's a distinction in terms of the way that the active electrophile forms depending on whether it's a primary alkyl halide or secondary tertiary. All right, so what happens next? Let's go through an example that shows a substitution reaction from start to finish. And I'll pick maybe the ethyl example, like where the ethyl has been activated by the aluminum chloride. So here is how that would work. So this would be step 2. Ring, electrons, pi electrons. Attack the electrophile. So here's a benzene ring. I'm gonna, sorry, feedback, chalk feedback. Here's our ethyl chloride that's been activated by aluminum chloride. It's a primary alkyl halide, so it's got this structure. It doesn't form a full carbocation. It hangs out in that state with a strong partial positive charge on that carbon, and the ring electrons go and they attack there, and this super leaving group, maybe I'll lasso it out one more time with the orange chalk just to point out that it's a good leaving group. The leaving group leaves, and the carbon of the ring takes its place. So now we get the R group attached to the ring at this point, and there's a carbocation there. And the counter ion is aluminum with 4 chlorines attached and a formal minus charge on the aluminum. Sorry about that. All right, that's step 2. Step 3 then is this non-aromatic intermediate gets deprotonated. So I'll write that over here, and we'll keep going with the mechanism from left to right. Step 3. Weak base deprotonates. The electrophile. And here, our weak base is going to be this aluminum with the 4 chlorines attached. The base is any one of the chlorines. All you have to do, and you can pick on any one of them you want, but I'll start an arrow here. Just start an arrow at any one of the aluminum chlorine bonds and show it going over to here to grab that and go like that. Okay. Then what you get is this. The alkyl group has been added. We have a new aromatic ring, and we have an HCl. And we also get the aluminum chloride back. That is the full mechanism. So we get an alkylated benzene ring. Over here, if it were tert butyl cation, if you have a secondary or tertiary alkyl halide, the ring electrons, instead of attacking here, they just like attack here. And you get to a non-aromatic intermediate that would look very, very much the same. It would just have a different R group. So that's Friedel-Crafts' alkylation mechanism. There are some issues with this reaction, though. So let's talk about some limitations. There's always a catch, unfortunately. And here, there's a bunch of like issues with Friedel-Crafts reactions. Here's the first one. Issues with Friedel-Crafts alkylation. Number one, it only works with alkyl halides. So it really has to be an sp3 hybridized carbon to chlorine bond. For example, things that don't work, here's what you need to have. You need to have this. This is an alkyl chloride. So this is good. Things that are no good are, for example, aryl chlorides or vinyl chlorides. These don't work because the carbon here is sp2, the carbon there is sp2, and those just don't form carbocations or carbocation-like species that really are at all stable, and so they just don't form to any significant extent. It's really hard to make a carbocation at an sp2 hybridized carbon, so they just don't do this kind of chemistry. So it's really got to be an alkyl halide. So there's that. And then the other thing is that one of the things we know about carbocations from last semester is that they tend to rearrange. And it's still a problem this semester. It's the nature of carbocations is they're kind of complicated. And so this is issue number 2, is it's carbocation rearrangements can occur. So you probably remember this from last semester, or it probably sounds vaguely familiar, but here's an example of how it can complicate Friedel-Crafts alkylation reactions if you're trying to do one of these. If you put benzene or some other substituted aromatic ring in with this molecule, chloropropane, 1-chloropropane, and aluminum chloride, you might be hoping that you get a propyl group on the ring. So, maybe you'd be hoping you would get this. The problem is, if you do this reaction, you don't actually observe any of this. What you form instead is this. Isopropyl benzene. This is the only major product, organic product. You also get out HCl. So what's going on here? We start with chlorine on the end of a 3-carbon chain, but then it ends up being attached to the ring through the middle carbon. This is the kind of thing that if you see it, start thinking about rearrangements, reactions that can shift the position of the reactive site. And so here's what's going on. The chloropropane reacts with the aluminum chloride, as you would predict based on what we've talked about. Aluminum chloride is very electron poor, and the chlorine is electron rich, and so they like to get together and form a complex. And then that complex looks like this. It's got the aluminum attached. There are 3 chlorines. There's a formal minus there and a formal positive there. And I'm just going to draw in the H's on these carbons to indicate what happens next. So there's a strong partial positive charge right here on this carbon. That carbon is kind of like a primary carbocation. So I'm going to say this is a primary carbocation-like species, which is unstable because primary carbocations aren't very highly substituted and the positive charge doesn't have a whole lot stabilizing it. So it goes through a rearrangement process. It could become more stable if the positive charge were more substituted on a more substituted carbon. And the way that happens is one of these H's next door hops over with a pair of electrons. And this is called a 1,2 hydride shift. 1,2 hydride shift. And when your 1,2 hydride shift happens, the position of the charge changes. So now, instead of positive charge being on the end carbon, there's positive charge on the middle carbon, and this is the electrophile that the ring actually sees. And there's an aluminum with 4 chlorines attached and a formal minus charge. So this is the actual active electrophile, and then the ring attacks it, and that's how you get the isopropyl group on the ring instead of the propyl group at the end of the chain, like a normal propyl group. So the take-home message is that whenever you form an active electrophile in Friedel-Crafts alkylation reactions, you have to worry about carbocation rearrangements. Let's look at a couple. This is a 1,2 hydride shift. You can also get 1,2 alkyl shifts. So I'll show you one of those as well, just so that you've seen it. And then there are going to be examples of these in the homework, so you can practice this. Get refamiliarized with carbocation rearrangements. They're kind of a pain. You know, but it's just carbocations are such reactive species that they, you know, they don't wait to see a benzene ring all the time. If they can find a way to become more stable by rearranging, they will do that before they even have a chance to bump into a ring. So here's an example of another kind of reaction that uses let's see here. I'm going to think about putting an alkyl group on this ring that's got this kind of substitution pattern. Okay, and aluminum chloride. And what comes out of this is not what you'd expect. You don't get CH2C with a tert butyl group. This actually doesn't form to any extent, because what happens is the active electrophile, and what I'll do is I'll draw it down here and show you what the carbocation rearrangement produces. All right, so here is the alkyl halide that we start with. I just turned it around. It bonds to aluminum. which activates it and makes it into an even better leaving group. But then what happens, before a ring can even come here and react with this thing, there's a 1,2 alkyl shift that happens. So one of the methyl groups migrates over with its pair of electrons, and the leaving group leaves. So what this forms then is a new active electrophile. We get this. So it's a tertiary carbocation. Now, instead of over here, what we had was primary-like. So that's why this rearrangement wanted to happen, is it generates a much more stable carbocation compared to what we had. So this is what the ring actually sees, and when the aromatic ring attacks it, it attacks that carbon. And the result is the aromatic ring ends up with an alkyl group on it, but this alkyl group has got the following structure. Methyl group here, methyl group here, methyl group here, and methyl group here. And that looks pretty different from the alkyl halide that we started with, because the skeleton of the alkyl halide is actually rearranged. The carbons are connected differently. So that's the result of this rearrangement. This is a 1,2 alkyl shift. So a couple of different kinds of rearrangements that can happen. And so what I would recommend is that whenever you see a Friedel-Crafts alkylation reaction happening, take a minute and look at the active electrophile that you've drawn. I mean, think about it, draw it, and then ask yourself, is there a way for that carbocation or carbocation-like species to rearrange? And if there is, it will want to do that, and it's going to produce a new electrophile that's the one the ring's going to really react with. So, all right, just a detail you got to manage. And then on to actually a simpler type of Friedel-Crafts reaction, the Friedel-Crafts acylation. By the way, there are more limitations of Friedel-Crafts alkylation reactions. We're going to talk about those later, but we have to talk about substitution effects before we can understand those. Yes, there's a question.
So with the 1,2 alkyl shift, I think if I'm counting right, there's only 5 carbons like when we first react, and there's 6.
Okay.
So where did like the other
Okay. Yeah. Yeah. I'm sorry. There's supposed to be. Yep. This is a good point. This is. So the question is about, there's an error in my structures over here. So let's go back to this. And yep, so this molecule only, this alkyl chloride only has 5 carbons in it. And I drew a methyl group over here by mistake. There should not be a methyl group there. That should be an H. And then in the final product, there should not be a methyl group there. It should look like this. Thank you. Yeah, that's important. Otherwise, you'd probably be confused. It doesn't grow a carbon anywhere. So yep, that's the danger of inventing examples on the fly. Sometimes you make a mistake along the way. So thanks for catching that. Awesome. All right, let's go talk about the Friedel-Crafts acylation reaction. This is the other type of Friedel-Crafts reaction. FC for Friedel-Crafts acylation. And we're going to talk about its mechanism here. So it starts with an acid chloride, and acid chlorides have this structure. They have a carbonyl that's attached to a chlorine, and then there's an R group. And they get put in with aluminum chloride. I'll draw that aluminum chloride with its partial positive charge on aluminum and partial negative charge on the chlorine, which causes them to want to get together. The chlorine attacks the aluminum, and you get this complex where we've got a chlorine that's bonded to the aluminum. This is kind of the common theme here that we're looking at, is we've got a Lewis acid that goes and latches itself onto a halogen to make it into an even better leaving group. So again, I'll highlight this as a super leaving group. And this complex does not stay as I've drawn it for any length of time. It's really reactive, and what happens is a pair of electrons on the oxygen swings down to form a new oxygen-carbon triple bond, and that gives the leaving group a push. So that gives this active electrophile that looks like this. This is called an acylium ion, which is an ion that we've seen before. That was in mass spectrometry when we looked at how ketones fragment and sometimes aldehydes and esters. They form these acylium ions that are highly stabilized by resonance, and it gave rise to peaks at like 43 and 57 and all kinds of really strong base peaks in mass spectra of molecules that contained carbonyls. That's one resonance structure of it. The other resonance structure, which you could draw, would be if you take a pair of electrons out of the triple bond and give them to oxygen, you could generate this other resonance structure, which is just another way of describing the molecule and its structure. So these are resonance structures. I'll put brackets around them. And when you're doing the homework, I noticed that Alex was a lot of times with these acylium ions would be working with this. So just remember, it's either this or this. This is actually a better, more stable resonance structure because all the atoms have octets. This resonance structure, the carbon lacks an octet, which makes it a lot less stable. But either one of them could be used in a mechanism. They're both representing the same molecule. So that's a bit about this active electrophile. And the thing about this active electrophile is that since it's resonance stabilized, it doesn't rearrange, which is a really nice feature. Acylium ions are resonance stabilized. And do not rearrange, which is a really handy thing to have, behavior to have. So it's nice. You don't have to worry about, is this acylium ion going to rearrange to become something different? It stays right where you put it. So you can always count on it being right where it forms. So, and it's resonance stabilized. Okay. Let's talk about some substituted benzene things. We've got a few minutes. We can talk about some substituted benzene chemistry. And this is where it's going to start to get more interesting, I think. We've laid down 5 different reactions that we've studied. So we studied chlorination, bromination. That's actually one reaction, I would call it. Nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, 5. But now we're going to address how do they work when you have a group on the ring. So far we've just talked about them with benzene. But substituents have a big impact on how these reactions work. So this is our beginning of a unit on substituted benzenes. And how they behave in Friedel-Crafts electrophilic aromatic substitution. So substituents on aromatic rings have 2 effects. On electrophilic aromatic substitution, on electrophilic aromatic substitution. Effect number 1 is they make the reaction faster or slower. So at the beginning of the lecture, I put up that group of activating groups, that list of activating groups and deactivating groups. If the ring has an activating group on it, something that pushes electron density into the ring, that makes the reaction faster. And if they have a group on the ring that withdraws electron density away from the ring, they make the reaction slower. So they either speed up or slow down the reaction. The other thing they do is they direct which atom the ring reacts with, or they influence, direct the substitution to certain ring positions. So the substitution is not random. It depends on the nature of the substituent, whether the substituent likes to direct to the ortho or para positions or the meta position. So we're going to see an example of that. I'm going to put how methyl influences the reaction. This will be the first one we look at. So that molecule is called toluene. We learned about that in the chapter where we were studying aromaticity and naming of benzene ring compounds. So what happens when you put toluene into an electrophilic aromatic substitution reaction with, say, I don't know, nitration type conditions? HNO3, H2SO4. So you'll need to know that these are conditions that put nitro group on a ring. And this is toluene. And what can come out of this is 3 different reaction products. You can get toluene with a nitro group in the ortho position. You can get toluene with the nitro group in the meta position. Or you can get toluene that has a nitro group in its para position. Those are the possibilities if you're talking about how you can add one group, a nitro group, to a ring that has a methyl on it. Here are the results. Toluene nitrates 25 times faster than benzene. So the first thing you'd notice is that if you were doing reactions on benzene and then you switch to toluene, is the reaction gets done a lot faster. It's 25 times faster, which is a lot. And then the other thing you would notice is that ortho and para products are major. Meta is minor. So you get a lot of the ortho and a lot of the para, but just a little bit of meta. We used to actually do this experiment in the organic lab, and we do a GC chromatogram of the product mixture, and we see a big peak for ortho, and then a little peak for meta, and then a big peak for para. And so you might be wondering, why does it do this? Statistically, if you look at the number of positions on a benzene ring, there's 2 ortho positions, there's 2 meta positions, and there's 1 para position. So you might expect a 2 to 2 to 1 ratio of products statistically, but that's not what you get, not even close. The para position is, there's only 1 of them, but it's sterically a little bit more accessible. The ortho position, there's 2 of them, but it's sterically a little bit more congested because it's really close to the methyl. But the meta, there's 2 of them, and they're not at all sterically bothered by the methyl group. So why is there so little reaction happening at the meta position? And the reason is the way that the alkyl group donates electron density in. So it's pushing electron density in, which makes it an activating substituent. So here I'm going to say alkyl groups are activating. They push a little bit of electron density into the ring, and what it specifically does is it puts electron density preferentially in the ortho and para positions. So the ring develops little bits of partial negative charge on these positions as a result of the methyl group being here, pushing electron density in. So these are spots that are a little bit more partially negative. So when they see a nitronium ion electrophile, remember the whole idea with electrophilic aromatic substitution is you got an electrophile that's really, really electron poor, and it sees partial negative charges on the ring. That's where it's going to want to go. So that's why you get ortho selectively and para selectively, but not so much meta, because meta isn't activated the same way ortho and para is. So, so what we say about alkyl groups is they are activating and ortho-para directing. So when you have an alkyl group like a methyl or an ethyl or a propyl or any alkyl group, count on it activating the ring, making the reaction go faster. Whatever electrophilic aromatic substitution reaction you're talking about, could be nitration, could be chlorination, sulfonation, whatever. It's going to make the reaction faster, and it's going to make the reaction want to happen ortho and para. When we come back on Monday, we're going to talk about all the other substituents that are possible that you might see and what exactly they do and why. So have a happy and safe Halloween, and I will see you on Monday.